I'm Charlie, and this presentation will be a mixture of low-level programming, general multi-threaded tips, and compile extensions. So, to begin, there's NumPy, or JSON, cryptography, Pydantic, Polars, Pandas, SciPy, PyYAML. These popular libraries. Who amongst you has never heard of even one of them? Well, figured as much. So all of these popular libraries share one thing in common. They do not contain pure Python code. They instead contain compiled extensions, which either wraps around libraries written low-level programming languages, or has logic written in such languages or in snippets for performance, such as for data processing. So, for those unfamiliar who don't know what a compile extension is, here's a very simple toy example. In the top left, there's a C function that merely wraps over other more primitive C functions. That all it does is generates a random integer. Below that is a Py method def structure that lists all the methods that will be exposed to Python, such as the method's name, what kind of function that it is, what kind of arguments it takes, any doc strings, etc. Right next to that is Py module def, which provides metadata about the module to be imported into Python, such as, again, its name, what functions are available within that method, any doc strings, etc. And after that is a module's entry point, so to speak, the Py in a double underscore module name, the module name, so to speak. So, any modern build tool can be used to create compiled extensions, but for the sake of simplicity, let's assume setup tools. Is anyone else planning to jeer at it for even me suggesting setup tools? Okay, so the bare minimum within a setup.py file contains this. The relevant parts is the ext modules attribute, which contains a list of extensions to be compiled, and within the extension attribute, it specifies the name of the extension and what source files comprise it. And doing all of this merely does all of this. So any sufficiently complex compile extension will invariably export objects that may be concurrently modified by multiple threads, and that inevitably involves the GIL or the global interval lock. In this diagram there, the thread spindle represents a thread running code inside a native extension. Within that is a lock, which represents a thread attempting to grab access to the GIL. The unlock symbol indicates that the thread holds a GIL, and within the regular Python interpreter, only one thread that has access to GIL can directly call the C API. Even with the GIL, parallelism is possible so long as there are threads not waiting to acquire the GIL. For instance, any thread performing I/O or a long-running calculation that does not require any state or functionality from the C Python runtime. Okay. So there are a few current approaches to sidestep the GIL. The first one is the multiprocessing module, which spins up a process containing a new copy of the Python interpreter and its own GIL. The downsides is that one, spinning up a process is much more expensive than spinning up a thread, and two, to share data between these subprocesses, either some sort of serialization or shared memory approach is required, further increasing overhead. The second main approach and the second alternative is for the compiled extension to manually release the GIL, and this is not particularly scalable, especially in scientific computing. In fact, the many hoops that these popular scientific libraries have to get around the GIL is one main reason why the free-threaded interpreter even exists. So, what is the newfangled free-thread interpreter, you may ask? Well, okay. In this new diagram, the GIO is completely absent. So there are no lock icons located on the spindles. Because there is no GIL, the various threads do not have to wait to acquire in order to do I/O, make native function calls, or most importantly, call into Python C API. To explain the changes to the interpreter in detail would definitely warrant a 1 hour long presentation. But the gist of it is a change in Python's memory. The interpreter's memory allocator allows objects to be garbage collected without maintaining a linked list, and that built-in collections such as dict, sect, Python's dict, sect, and list, etc., don't have to be logged in read-only operations. The second major change is changes in how the interpreter manipulates the reference counts of Python objects. To put it very simply, in the free-threaded model, the reference counts of those objects are modified less often, thus reducing thread contention when those objects are modified by many concurrent threads. Okay, to elaborate I made in the first point, this also introduces container-level thread safety as replacing the GIL as those collections have their own lighter, more fine coarse logs, which only need to be logged during modification. The fourth major change is in the introduction of critical sections. With the elimination of the global interpreter lock, using those reduces the frequency of locking, and unlocking in nested operations, and it permits much more fine-grained per object locks. Now, on to porting tips. This will heavily emphasize more practical porting tips than theory. So the simple toy example that I provided uses what's called single phase initialization, and it's slowly being deprecated in favor of the more modern multi-phase initialization. In single phase initialization, to mark your compiled extension as free-thread compatible, all you have to do is within the PyInit's double underscore entry point, with that particular macro, if that's a particular macro PyGIL disabled, you simply call the CAPI function PyUnstable module set GIL yada yada yada. For multi-phase initialization, it is slightly simpler. In the PyModule dev slot, only the developer all has to do is simply add a PyModGIO slot with that same PyModGIO not used, and simply include the PyModule dev slot array assign that array of slots into PyModule dev. Okay, who here has written a single line of Python code? A few of you. All right. For the rest of the uninitiated, Python is a language whose syntax is a superset of Python that supports directly calling C or other C or C++ functions, and can annotate variables and class attributes with static type declarations. This is quite helpful for generating efficient code, as it allows the Python compiler to not have to guess the exact data type of those variables and class attributes. So. Making your extension module written in Python, it depends on which build tools you prefer. If your project still relies on setup tools, all you have to do is do this. And if your project relies on Meson, you only have to write this with considerably less boilerplate. If your native extension uses PyBind 11, which is a C++ based more ergonomic wrapper of Python C API, then all you have to do is annotate the PyBind 11 module function with PyModGIO not used. For Rust projects, I know, I speak from experience. Then all you have to do is mark either the native Rust module or a function with the annotation py03 PyModule GIO used equals false. And let me ask one more thing. Who amongst you still has heard of Swig at all? Who amongst you have written Swig bindings? I mean, fair enough. Who would be sane enough to use Swig in this day and age? Okay, so all right, so generally to ensure threat safety and to ensure threat safety among multi-threaded programs, it is preferable to migrate global state away to thread local data. There are a few ways to achieve this. For native Python and Python code, there's the built-in threading.local. And for C or C++ project, C++ code bases in general, you can annotate your variable with the thread local keyword. With the free-threaded model, the Python C API offers PyTexas, which allows you to bind thread local state to a unique handle, so to speak. All right. Alternatively, if you decide that keeping a cache visible to the entire program is necessary, there are two ways around it. One, if it's not performance critical, just outright disable it. The second way, and this only works with single phase initialization, is to initialize the cache within the Py in a double underscore entry point. Here, with these two macro functions, lock and unlock, and if you compile this with the free-thread interpreter, these macros expand to calls to PyMutex to lock and unlock the mutex. Okay, so all right. So as I said before, Python's dict, set, and list objects have their own lighter internal logs. Now that the GIL has been dispensed with. Consequently, any C API function that operates on those objects because those data types are implemented in C are automatically thread safe. The major exception is PyDict next, which simply gets the next key value pair within a Python dictionary, and it's highly recommended that you wrap any calls to that function with those critical section function macros. Now, what are those critical section macros? Unlike a more traditional lock, which such as GIL, critical sections do not guarantee exclusive access throughout the entire duration. When a thread acquires a lock associated with a critical section, which is done implicitly when a thread calls a thread safe C API function, it attempts to acquire the underlying mutex. These critical sections help ensure that you avoid deadlocks due to reentrancy and lock ordering. And it comes in two forms: the PyBegin critical section and PyEnd critical section for locking one object, and another version for locking two objects simultaneously. To elaborate on preventing deadlocks, critical sections if a thread tries to acquire a lock that's already been held by another thread, it first automatically suspends all active critical sections, temporarily releasing the locks. And when a blocking operation such as I/O completes, only the topmost critical sections is required first, this is a rather useful property if you're locking two objects simultaneously. Now, on to continuous integration. For any GitHub projects, there are two GitHub actions that can make sure that any future pull requests are compatible with the free-threaded interpreter. There's a set of Python where all you have to do is include a Python version that ends in a T, and there's CI build will, which automatically builds binary wheels targeting a wide variety of CPU architectures, OSs, and Python versions. All you have to do is set these two environment variables to these values. Now for unit testing. There are a few plugins that target PyTest and the standard unit test to make your existing unit test compatible with the free-thread interpreter. Note that PyTest is not thread safe, and according to the maintainer, will never be made more thread safe. This is mainly due to the fact that a wide variety of PyTest-based projects and PyTest itself relies quite heavily on shared global state. Consequently, any PyTest-based test suite has quite a bit many caveats. Now, another helpful set of tools are instrumentation libraries that all three major compiler tool chains support: GCC, Clang, and even MSVC. Those are ASAN and Address Sanitizer, or ASAN, or Thread Sanitizer, or TSAN. ASAN checks for out-of-bound accesses to the heap, stack, and globals, and TSAN checks for data races among various threads. By default, if a violation occurs in either one of them, it immediately aborts. Okay, so see x pointing PyGIL equals 0 in our variable make sure that the GIL is completely and utterly turned off. Even if your Python project imports a module that is not explicitly marked to be no-GIL safe. This is quite useful when using debuggers such as GDB, LLDB, or even SciGDB for Python-based extensions. Furthermore, there is a useful open source project called C Python Sanity, which provides pre-built Docker images of the Python interpreter itself with TSAN and ASAN enabled to help you jumpstart testing a product for databases and out of bounds check without having to build the Python interpreter itself from source. Okay, I believe we're almost out of time, so I can't go through this here. So, in closing, if you scan the QR code right in front of you, it would take you to a website made by Hugo van Commande, a core developer of CPython, which will show you which of the popular PyPI packages containing compile extensions are verified to be free threaded compatible. All right, so. For those among you who still doubt either the usefulness of the presentation or my expertise on the topic, please feel free to scan that QR code right there. It will take you to a gist page containing all the commits that I've made to various repositories to improve free-threaded support. Please, I dare you. And remember, bump your dependencies because they may implicitly make your project free threaded compatible. And my sources.